Why? In operating system, paging is the subject and paging is the concept where you are getting stuck. What is virtual address space? Physical address space? Minimum number of bit required for virtual address space? Physical address space? What is the offset? How many bits will be there for offset? And after that, how to calculate the page size? How to calculate the page table size? Means what will be the size of the page table? And after that, what will be the internal fragmentation also? For this type of question, you are getting confused, right? So that's why I am here with this video, and after watching this video, this concept will be very easy to you and you will tell me how you are feeling. And after watching, definitely you can subscribe to the channel and click the bell icon to get all the latest update and notification. So see that. Here we are doing first of all what is the requirement of paging, that is the very important to understand. So here is the secondary memory. Normally our secondary memory size is very high because our hard disk, secondary memory is what? That is our hard disk. So it can be 1 TB size near about. Next thing is our main memory. So here is the main memory. Normally main memory means what? Normal main memory is our RAM. What will be our RAM size? Maximum it can be 16 GB or something, right? Now here is the CPU. So CPU is from where CPU will execute each and every program? From the main memory, because the secondary memory speed is very slow. So we are sending some of the part of the program to the main memory, and after that CPU will execute it. Now here the concept is coming, how we will send. The paging is the concept where each and every program, because program is the process, program in execution, that is called the process. So you wrote a program, maybe the size is 10 KB, that is a process 1. Now what we will do, we will fix a size. What is the size? We will fix the size, that is the page size. And always the page size and the frame size will be same. Page size and frame size will be the same. And that is called actually the offset. What is page? What is page? Page is actually divided into the secondary memory. We will divide the secondary memory into a same size of slots. These are called the pages. Okay. And the main memory also divided with the same size of slots. These are called frames. So secondary memory is divided into pages and main memory is divided into frames. Clear? Now thing is, how many pages will be there and how many frames will be there? See that. How many pages will be there, that is depending on the process size. Because for each and every process we are dividing into some pages. In your secondary memory, that is in your hard disk, lots of program are there. So each and every process we will think about separately. So see that. Here it is your 10 KB. If I am thinking that each and every offset means size is 1 KB, that I am fixing. So how many pages will be there? 10 by 10 by 1 KB, that is 10 pages. So there will be the 10 pages. So here are the pages 1, 2, 3, 4 till 10. Now the thing is that main memory. Now main memory, for this time being I am thinking that there is not 16 GB space is not there. At a time I can take, maybe here it is a 5 KB space is there in the main memory. So main memory will be divided as per that how many frames will be there in main memory. That is depending on the main memory total size. The total size of the main memory is, for now I am thinking it is 5 KB. And what is the size of each and every frame? That is 1 KB. So in the main memory, how many frames will be there? There are 5 frames. Now see that I want to execute the process. But the problem is that in the process there are total 10 pages. But in main memory I can allocate only 5 frames. So at a time I cannot allocate everyone. Some of the pages I will send here. What are the pages? That is depending on my criteria. And it's not like that every time I will get all the frame free also. Because it is not like that. In main memory I will execute only my process. There are multiple processes. So main memory have to give the space to each and every process. That's why it's not like that every time it will be free. For now I am getting that 5 KB space free and there are 5 slots are free. Maybe this is frame number 1 is free, frame number 2 is free, frame number 2 is not free, 2, 3 is blocked, maybe 4, 5 and 6 and 7. These are free here. Okay. So what I am doing, page number 1 I am sending to frame number 1. Page number 2 in frame number 2. Page number 3 in frame number 5. Page number 4 in frame number 6. And page number next one, that is page number 5 in frame number 7. These are previously blocked. It was previously blocked. Okay. Now, for now I am telling these are previously blocked. So now what it will be? See that. Here is the page table. Now here is the page table. So this is my page table. Okay. And here you will be confused. That's why I am telling here are 7 KB. Okay. For now I am telling it is 7 KB so that there are 7 frames was there. But out of 7 frame these are already allocated. And now this 5 frame I got free. And in this 5 frame I put this. Okay. So that you will be no confusion. Now what will be the page table? In the page table we will store according to the processes. Per process, how many pages was there? 10 pages was there for this process. So this page table is for the process number 1. For this process number 1, I am taking a page table. In this page table, number of entry is depending on the number of pages. So in the page table, number of entry will be depending on the number of pages. There are 10 pages. That's why 1, 2, 3 till 10. Total 10 entry will be there. Now, outside there are 10 entry means it is indexing like 1 to 10. Now, inside what I will store? Inside I will store the frame number. So, in the frame number, page number 1 was stored in frame number 1. Page number 2 was stored in frame number 4. Page number 3 in frame number 5. Page number 4 in frame number 6 and so on. In that way it will be coming. Right. Now think that CPU is always sending the logical address. In the logical address, CPU know the page number. CPU know the page number and what? That is offset. Now what is offset? Offset is actually what? Offset is the size. Means what it is? Think like that. It is your copy. Okay, it is your copy. Copy means a book. In your book it is a page. Now in the page so many things are written. Now you take a Xerox copy. Now in this Xerox copy, whenever you are taking the Xerox copy, then also same thing will come here. Right? So size means size of the page will be same. Like if you are taking the copy, if you are taking the Xerox copy, that will be same. So if the line number 10 I want here, in the Xerox copy also line number 10 will be there. The page number 10, it is maybe the page number 10. So you take the Xerox copy of page number 10. In page number 10, if I am asking you for line number 10, so line number 10 will be here. If I am asking for line number 2, line number 2 will be here. If I am asking for line number 20, line number 20 will be here. So that is the offset. That's why what will be happen? Page number 10, you took a Xerox copy, that is okay. But in a book, there was 100 pages. Okay. Out of the 100 pages, your teacher told you to take the Xerox copy for page number 10, 20, 30 and 40. Now you take only this 4 copy. So when you take only this 4 copy, where you will store? Here in this folder you will store. So in the folder number 1 you store the page number 10. Folder number 2 means in the folder, this is the number, you store page number 20. Here 3 you store page number 30. Here in 4 you store page number 40. Right. Now see, when your teacher is asking that open page number 10, that is the CPU. CPU asking you open page number 10, and in that page number 10 maybe line number 2. Now you don't have the book. What you will do? You will go to your folder. In this folder you are maintaining an index here. This is your page table. You are maintaining the index here. You know that yes, page number 1 to page number 100, that is okay, but I don't have everything. I have the page number 10 in my page number 10 is there in frame number 2. So where I will go? I will go to frame number 2, and after that I need the line number 2. Line number 2 will be same thing. There is no change. So ultimate changing is what? Ultimate change is that according to this page number 10, I need that frame number, and this is actually same. This is called the offset. The offset will be same. There is not required to change any offset. Offset will be same here. Okay. So I hope it's clear to you what is going on here. Just take a page. If you are taking the book or if you are taking this copy, for this copy, if it is a copy, think like that. I am making the Xerox copy of this one. So the Xerox copy will be same. The line number will be same. So that's why offset will be also same. No problem. So now this is going on in this page frame, right? So when I am taking that page frame and offset, the page table, why the page table will be required? The page number will be converted into the frame number. Here I need the maybe page number 2. I need page number 2 and offset number 4. So what it will get? The page number 2 is in frame number. I will get here that the frame number is 4 here. From frame number 4 you can get, and offset will be same as it is, that is 4. So now CPU will go to here, that is okay. Frame number 4 I can get the page number 2 and offset will be same. No need to change anything. This is the thing going on, and this is called the logical address and this is called the physical address. Logical address means that is page number and offset, and physical number means that is frame number and offset. We are changing the page number to, so what it is? Logical address and the physical address. Logical address, there will be the page number and offset, and after that in physical address there will be frame number and offset, right? Now see that offset will be always same. Offset will be always same. Offset means the size of the pages. This is the size of the page and this is the size of the frame, and this is always same. So no problem here. Only the problem is here page number and the frame number. This will be converted through the page table. I will send here page number and from here I will get output as a frame number. I will go to that frame number. This is the thing. Now the thing is that logical address space and physical address space, how to calculate? That is how many bits will be required. Now we will work on bits. How to calculate the number of bits for logical address space and physical address space. So how many bits will be there? See that. When I am storing here the page number. So page numbers, to store the page number, how many bits will be required? Here the concept is like that. If I am telling you, you have to represent 0 to 7. 0 to 7. It is binary, right? So 0, 0, 0, 0, 0, 1 till 7 means 1, 1, 1. So to represent 7, how many bits are required? 3. If I am asking you, you need to represent 0 to 15. How many bits will be required? 0, 0, 0, 0 to 1, 1, 1, 1, that is 15. So how many bits are required here? There are 4 bits required. How to get it? It is actually the concept of log. Log means if there are total range is 8. Here the total range is 16. So 8 means what? 2 to the power 3. So how many bits are required? 3 bits are required. If there are range 16, then how many bits are required? 2 to the power 4 means 4 bits are required. If it is 32, then how many bits will be required? 2 to the power 5 means 5 bit will be required. 64 means it will be 2 to the power 6, that is 6 bit is required. And same way you have to go for 1024 means that is 2 to the power 10, that's why 10 bit will be required. This is the concept. You have to remember till 2 square, then 2 cube, then 2 to the power 4, then 2 to the power 5, 2 to the power 6, 2 to the power 7, 2 to the power 8, 2 to the power 9 and 2 to the power 10. Throughout the computer science, this is very important. How many bits will be required? Not only in computer science, everywhere. Okay, so must remember that. Now after that, so here if I am telling you that I need to page number, what is the range of the page number, that is means number of pages. If there are 512 pages total, so how many bits will be required? 2 to the power 9 means 512. So I need 9 bit. Now you will tell me, ma'am, in between something is coming. If I have to represent 80 pages are there, then how many bits? Always take the upper bound, because 2 to the power 6 is 64. It cannot do 80, right? So 2 to the power 7 is 128. So I will take here 7 bit. Always take the upper bound. In lower bound you cannot do. So that's why for 512 pages I need here 9 bit. Now offset is also depending on that size. If your size is, now it will work on the size, right? So size means offset. So size means offset means how it will be. What is that? Size, what it is? 1 KB, 1 GB, 1 KB. After that it is coming 1 MB, 1 GB, 1 TB. 1 KB means, and B means what? B means actually byte. Byte means, that is, byte means 8 bit. 8 bit means 2 to the power 3. That is bit. Okay. Now we are coming to byte. Byte means 2 to the power 10 byte. MB means 2 to the power 20. GB means 2 to the power 30. TB means 2 to the power 40. Right? So if it is given like that 16 KB. So how many bit will be required? 16 means 2 to the power 4. Multiply into KB. 2 to the power 10. So how many bits? 2 to the power 14 means from here I can get 14 bit. Got it? If it is given like that, maybe 32 GB. So 32 GB means what? 2 to the power 5 multiply into 2 to the power 30, that is 2 to the power 35. So here 35 bit will be required. That is the simple way what you have to do. Just whatever is given need to convert into the power, and it is KB, GB, MB, convert into 2 to the power, then add it, because 2 to the power m multiply into 2 to the power n, that is 2 to the power m plus n. That's why we are adding this number, right? So here whenever it is given like that, page size and frame size, it will be same. Because the page size, if you can calculate page size, then frame size, here offset. This offset and this offset will be always same. If page size is given, that is frame size. If frame size is given, that is page size. So offset is depending on the size. Convert the size into 2 to the power n, and then number of bit will be this n bit. Clear? Now what is the frame? So here frame number we will store. So it is also depending on how many frames are there. If there is 32 frames, then how many bit will be required? 2 to the power 5, that is 5 bit will be required. So just this is the bit, how to get the bit, this is the way, that number of bit. Now total address space, what will be the total address space? If I am telling it is the 10 KB each and every one, so it will be also, or I am telling 1 KB, I am not taking 10 KB, 1 KB. If it is 1 KB, 2 to the power 10. So here is 10 bit, here is also 10 bit, and here I got the 5 bit. So 5 bit plus 10 bit, that is 15 bit here, and 9 bit plus 10 bit, that is total 19 bit will be there. So the logical address space will be 19 bit and the physical address space will be 15 bit. Logical address space means secondary memory divided the process. It is depending on the process. How many pages will be there, how to calculate the number of pages. Here also you will be confused. So how to calculate the number of pages? I am searching for some space. Yes. So number of pages equals to process size divide by offset. Offset means the size of the page. Offset means this is the size of the page, right? That is the number of page. And number of frame, how to calculate? Number of frame, how to calculate? That is the main memory size divide by offset. Size of the main memory total divide by offset, that is the number of frame. I hope it is clear. Now you can solve the question. So here a main memory management system, 64 pages are there and 512 byte page size. Physical memory consists of 32 frames. Number of bit required for the logical address and physical address. Easy. You can do it very easily. Right? The logical address space and the physical address space. In logical address space and physical address space, what we are storing? That is page number. And here we will store the frame number. Here will be the offset. Here will be the offset. So number of pages here 64 pages means 2 to the power 6. So 6 bit will be required to represent. 512 is the page size means 2 to the power 9. So 9 bit for offset. Here also 9 bit for offset. Same thing. 32 frames are there. 32 frames means 2 to the power 5. So 5. 6 plus 9 equals to, and 5 plus 9 equals to, that is the answer. So yes, your answer will be 15 plus 14. It's easy, right? Now see that. Here read the following. This is the question. Read it and do it. Consider the machine 16 GB main memory. 16 GB is your main memory. 32-bit virtual address space. Now the page size is 4 KB here and frame size on page size are same, that you know. Now what is the minimum number of bits needed for the physical address? It is asking you total physical address. Total physical address means what it will be? That is the frame number plus offset together. And frame number plus offset together means directly you can go from the main memory. Because when I am doing the number of frame, what I am doing? Main memory divide by offset I am doing it, right? Now when I will calculate the total, offset is already included here. So what I can do directly from the main memory, I can get the total size. So main memory is given here 16 GB. 16 GB means 2 to the power 4 multiply into 2 to the power 30. So it will be 2 to the power 34 means number of bit will be here 34. So your answer will be 34 here. Next one. So next one is asking same question. These are actually the UGC net question. These are asking on UGC net comprehension type question, means 10 marks was there, and it is 2021 question. Now see, find the number of pages required for the virtual address space. How many pages required for virtual address? How many pages? How to do? Here is given 32-bit virtual address space. Here total is given you 32-bit. In this 32-bit, some are allocated for the page number, some are allocated from the offset. And what is offset? Offset you can get from the page size. So that is 4 KB. So how many bits will be there for the offset? 2 to the power 2 multiply into 2 to the power 10 because KB. So it is 2 to the power 12. So how many bits? 12 bit is for the offset. So here it is 12 bit. Total was 32. So 32 minus 12, I will get here 20. So number of bit will be there 20 bit. Now 20 bit is required to store the page number. Same here we calculate the 20 bit. So how many pages will be there? That is 2 to the power 20. Two things are there. That is how many bit when the total number of pages are there. When the 8 pages was there, how many bit was required? That is 2 to the power 3. From here we got the 3 bit. So opposite thing we calculate here, the 20 bit is required to represent the page number. So how many pages will be there? Just opposite. When bit is given to you, then you need to do number of pages, means 2 to the power n. When the number of pages are given to you, you have to do the how many bits are required, then you will do log the number of pages. Means you will see that number of 2 to the power n, and after that n is the power, so n will be the number of bit, right? So that's why your answer will be 2 to the power 20. Now the next thing, it is the already we have calculated number of bits reserved for the frame offset. Last one only we have done here, right? You can see the 12 bit offset, page offset, frame offset is same. So that's why definitely same thing, answer will be 12 only for frame offset. You got it? Now see here, page table. What will be the size of the page table? So what we are storing in page? What we are storing in page? Page table. We are storing the number of pages. An entry, number of entry in the page table is equals to the number of pages. So just now we calculate how many pages are there total. 2 to the power 20 pages are there. What we are storing in the page table? We are storing the frame number. So how many bits are required to represent the frame number? How many bits are required to represent the frame number? That is the thing. How many bits will be required? Here we got already the from the main memory, that was the size, means the physical address space. Just now when we calculate the physical address space, that was 34 bit, and out of that offset is 12 bit. So remaining will be 34 minus 12, that is 22 bit is remaining from here, right? So 22 bit is there for the number of frame, right? So to represent the number of frame, 22 bit is required. So that's why what will be here? So here 2 to the power 20 and 22 bit is required actually. But in this question, no need to think about that. Because in this question it is already given that the page table is 2 byte. It is already given to you. Because in the page table we are storing frame number, that is okay, plus something extra, some extra information are also there, like that some bit, that is obsolete bit, are there or not. So in the page table some extra information is also there. So it is given that the each and every size of the entry is 2 byte. So directly you can calculate. In some question maybe it will be not given, then you need to calculate the bit of the frame number. But here in the question it is not required. If it is not given to you, then what to do? 2 to the power 20 multiply into 22 bit. This bit you need to convert in byte. 22 bit is near about 2 byte. Okay, so that's why you can think like that. Actually you have to take the upper bound, that will be 3 byte. So no need to confuse about that. Here it is 2 byte is given, just you will do 2 to the power 20 multiply into 2 byte. If it is bit, always remember I have to convert in byte, means I have to do 8, divide by 8, like it will be near about 3 byte then. But in question it is given 2 bytes, so we will work on 2 byte. Okay, otherwise it will be, answer will be different. So here I will multiply with 2 byte, then it will be what? 2 and 2 to the power 20 means, 2 to the power 20 means MB. So my answer will be 2 MB. It's very easy. Now the last question, what is the internal fragmentation of the process? Internal fragmentation of the process. So for that let's learn internal fragmentation and external fragmentation also. Internal fragmentation, external fragmentation. Here internal fragmentation means I have a 38 byte space, but I am placing here a process that is only 32 byte. So my wastage is 6 byte. This wastage of space is called the internal fragmentation. What is external fragmentation? Here I allocate a 4 byte process, that is P1. Here I allocate a process that is, okay, no, here maybe it is free. This is a free space. Okay, this is also a free space. Here I allocate maybe a 3 byte process. Okay, so this is free also, this is also free. So 4 byte is free here, 4 byte is free here. Now I have another process, that is maybe process 2. It's required a 8 byte space. Although you can see this 4 byte, 4 plus 4 byte, this is free here, but I am not able to allocate because it is not contiguous. In between, this space is already blocked. It is not contiguous. This is the problem of external fragmentation, and it can be overcome using compaction. Compaction will do that. It will take all the free places together, like it will free the 8 KB here, and after that it will allocate this 3 byte here. This is the possible through compaction. Now let's solve the question. See that here it's easy, internal fragmentation. What was the process size? Is 30 KB process size. For 30 KB process size, I know that page size is 4 KB. If I am dividing 34 divide by 4, it is actually 4 multiply 8, 9 means it will be 36. 4 multiply 8 means it will be 32, right? Now see that. If I am allocating all the 8, this is the space here. So yeah, here I am going, space is not there. So 2 KB will be the answer. Why the 2 KB? I am showing you. All the 8 will be blocked, right? 1, 2, 3, 4, 5, 6, 7 and 8. These all are the 8 will be total. I am not written 8. So it will be 4 multiply 8 means 32 total complete. 1, 2, 3, 4, 5, 6, 7 and 8. These 8 are all total completely 32. Now I need the 9th one also. And in this 9th one, actually this 9th one is how much? 4 KB. It is total 4 KB. But out of 4 KB, how much remaining? my total size was 34 minus 32, 2 kb is remaining only. So from here I will take only 2 kb space, and this 2 kb is wastage here. This 2 kb is actually wastage here. So answer will be 2 kb, that's why. That is the internal fragmentation. You can do this question in same way, that is 34 kb I require, means I need at least 9 pages. That is 36 minus 34 is 2 kb. In that way also you can do, but conceptually this is the answer. So those who are watching till now, please let me know in the comment section your idea is clear or not. And thanks for watching till now, till the end. Because lots of students are not watching till the end. They are leaving the video, and actually they have not that much patience to understand that concept. I want to see that, yes, who is watching till now till the end, and I am sure about that those who are watching till now till the end, their concept is full clear. And after watching this, you will be never confused about this concept. So let me know in the comment section, and please like, share to all of your friends and motivate me to upload more video. Thank you. See you soon in my next video.